In the previous section, we spent a lot of time talking about the fundamentals in AWS. As most of us are aware, AWS has the lion's share of the cloud market today. However, we are starting to see that shift a little bit. Azure specifically has matured over time and learned some lessons from AWS of things that work and things that don't. Whether it's because of enterprise relationships that a lot of organizations have with Microsoft or the plethora of platform as a service offerings, we're starting to see more and more customers leverage Microsoft Azure now. Similar to AWS, the way native constructs are used in Azure, as well as how those constructs are strung together for organizations to build out workload frameworks and infrastructure is different. They're called different names and they behave different across clouds. They also have different limitations and interact differently, so it's important to understand these fundamentals. What we will do in this section is take you through some of the Azure building blocks and basic concepts, not only from the resources that exist there, but how to get started in general form on an organizational perspective. As you look to go into Azure, there is an organizational structure that you need to understand prior to consuming resources and starting to build out frameworks. This structure is important as it forms the basis for building an RBAC constructs for your environment and sets the framework for how environment is organized. The top level of this organizational structure is something called an AD tenant. It is often used to identify the enterprise itself. In some instances, organizations will have a single AD tenant in which all their resources will be contained, and in other instances, they may subdivide that tenant into subdomains, like production or development. We can further split an AD tenant into subscriptions, which are synonymous with AWS accounts. Early on, the subscription architecture was really driven towards business units or environments. As this is another point of billing isolation in RBAC, it made a lot of sense for organizations to carve it up that way. As we're moving into Cloud 3.0 and organizations mature in the cloud, we're starting to notice patterns where some customers are creating a subscription per application to get more granular chargeback, RBAC, and visibility controls at the application layer. So what used to be 10 to 20 accounts or subscriptions now could be upwards of 50 to 1,000 as applications grow. Under subscriptions, we can further organize our resources within resource groups. A resource group is a mechanism which allows customers to bundle resources together in a common container for ease of management. This could be organized by application or even by environment and provide customers with flexible means of grouping resources together. Now that we have a good understanding of the top level organizational structures, let's dive a little deeper into the specific resources that we can actually deploy in Azure. When you look to deploy a resource in Azure, you will see services and resources. Services are used to categorize the thousands of available resources into classification groups to easily find what you're looking for. Examples of these categories include compute, networking, and storage. As we highlight a specific service, this then breaks down into available resources included in this category. In the case of the compute service, this would include things like virtual machine, availability sets, image versions, etc. We can then use the previous concept of resource group to take our disaggregated resources and bundle them up in a resource group for easier management and visibility. As we begin to scale our workloads, there may be multiple resource groups within our AD tenant or subscription, which houses multiple environments, applications, or any organizational grouping that we want. We can then expand any of these resources groups to view all of the individual resources which make it up. The resource group view would then allow us to see VMs, storage, accounts, etc. that make that up, as well as give us a point for building an RBAC control for these resources as a group. So as a review, we have the organizational components of AD tenants, the subscriptions, and the resource groups. Then as we start to deploy resources, which are categorized as services, we can then bundle those up in a flexible manner. Now, let's dive a little deeper into some of the networking components, as Azure provides a wide range of networking resources from basic building blocks to more advanced services and features. Obviously, we're not going to be able to go through all of these in detail today. However, some of our more advanced certification offerings, like the ACE Professional, provide a deeper dive into these constructs and the architecture supported. Today, we want to talk about some of the fundamental components customers will use when initially constructing their cloud network. The first basic building block we have is the VNet, or virtual network, which is synonymous with an AWS VPC. Similarly, Azure also provides functionality like availability zones. However, here's an example of where some nuances come in. Availability zones in Azure do not exist in every region, so you have to be conscious of what regions you're deploying your workloads to in order to see if they are available. In addition to that, certain components are availability zone aware, certain components are not, and certain components are global by default. For instance, the concept of a VNet as well as a subnet are automatically spread across availability zones and are not tied to an individual zone as some other cloud providers. Another basic construct is the virtual network gateway, which we'll talk about in a minute, which has the option to be deployed in availability zones based on the region selected. So when you deploy that top level resource, there are different SKU types, and of those SKU types, some options are available where you can deploy the gateways in the availability zone of your choice. As you're deploying resources within Azure, that's another concept that you have to be aware of. Certain top level resources are availability zone aware, while some aren't, and others do it by default. Another example of these nuances can be found with the basic component of public and private IP addresses. While AWS defines public and private subnets, you don't have that same concept in Azure. Subnets are private by default, and if we want to provide public connectivity, we can do that in a couple of different ways. In Azure, however, we don't have to assign a public IP address or an internet gateway to a VM to allow internet access. There are some native functions that allow a private VM to ride the underlying fabric and access the internet. There may not be consistency of IP address, and there may be some limitations in the available NAT ports, but these are some differences between clouds that can affect your architectural decisions. The virtual network gateways are another basic component previously mentioned, and they come in a couple of different flavors related to on-prem connectivity. There's a VPN gateway and an express route gateway. VPN gateways can support IPsec or point-to-site VPN connections, whereas the express route gateway is how customers terminate their dedicated express route circuits. We will go into more detail later on what an express route circuit is, but there are some unique requirements related to the gateways. The gateways themselves are deployed in VNets and require dedicated subnets. A predefined subnet must be created with a very specific name. For gateways, it's called a gateway subnet. A little bit later, we'll talk about what this actually looks like in deployments, but these are considerations you must be aware of when you're looking at VPN or express route connectivity to connect your on-prem facilities. There's a third gateway called a local network gateway, which is only applicable when standing up IPsec VPN configurations. A local network gateway is a representation within Azure of your on-prem IPsec termination point. Later, we'll talk about some transitive options within Azure, but one component in this category is VNet peering. This is the concept of peering two VNets together to allow communication between them, as VNets are not natively transitive within Azure. There are also multiple route tables within Azure that customers need to be aware of. There's a default route table as well as custom route tables, and these may also receive BGP routes from on-prem if VPN or express route connections exist. Another component is the NVA, or Network Virtual Appliance. The easiest way to think about an NVA is any third-party marketplace item. Common NVAs are firewalls like Palo Alto or Checkpoint or FortiGate, but they could just as easily be a Cisco CSR for routing. If we boil down these basic building blocks, most customers start with these components shown. Our virtual network is our private network with a top-level CIDR, which we can then subdivide into individual subnets. We may be required to create some dedicated subnets, like the virtual network gateways we mentioned previously, but we can also customize additional ones to our needs. Then there are route tables. We have a system default route table. However, we can create our own route tables and manually configure UDRs, or user-defined routes, which are static entries to overrule these default behaviors. For instance, we previously discussed a VM having internet connectivity by default. As you can imagine, this isn't a behavior a lot of enterprise security teams would be happy about. So we may want to insert an NVA or a firewall into the path before any VM is allowed to talk out to the internet. We would do that with a custom route table and UDRs to statically define a default route to the firewall. The other basic networking component is load balancers. Load balancers are used in Azure to provide basic HA for NVAs, as well as traffic distribution for VMs. Let's look at putting some of these basic components together to start building an end-to-end network. Starting from left to right, we have the customer on-prem network. On the customer edge, we can connect to Azure using IPsec over the internet or ExpressRoute for private connectivity. For ExpressRoute connectivity, this is accessed via provider like an Equinix or an AT&T. These providers can provision the circuit as either layer 2, in which they merely hand you a VLAN, or layer 3, where they handle all the BGP routing terminations and most often appear as a node off your MPLS backbone. One key difference to note on ExpressRoute versus Direct Connect, as an example, is ExpressRoute is delivered with 2 links by default. This is different than some of the other providers' private connectivity offerings. With each ExpressRoute circuit, there are 2 routers referred to as the Microsoft Enterprise Edge routers that sit on the Microsoft Edge and provide the BGP endpoints for the circuit. If you provision a 10 gig ExpressRoute circuit, you're going to have 2 paths which can be active-active that you run BGP across, and these terminate on those edge routers. We then terminate those ExpressRoute circuits on our virtual network gateways and our VNets. We can also have VPN circuits which terminate on a VPN gateway within the same VNet to provide secondary paths. Within our VNet, we have an example of an NVA. In this case, it's the native Azure firewall, but this could just as easily be a Palo Alto firewall or Cisco CSR. We also have another workload in a separate VNet, which is utilizing VNet peering so our VNets can communicate. This is a typical architecture known as the hub and spoke architecture, where we have a common VNet that contains some shared services with workload VNets peered to this hub VNet as spokes. These spoke VNets can leverage these shared services in the hub, including access back to on-prem. As our workloads begin to expand in Azure, transit networking becomes a crucial part of our architecture. We need to interconnect our workloads as well as provide access to common shared services, while still being able to do so in a controlled and secured way. Unlike AWS, where we have the concept of transit gateways, native transit in Azure is a little different and varies based on the traffic flows. We have options for intra-region and inter-region spoke-to-spoke communication, and these options can be used simultaneously to support customer needs. Let's walk through these options and the pros and cons of each. Our first option for intra-region connectivity applies when customers are leveraging ExpressRoute for on-premise connectivity. We can leverage the Microsoft Enterprise Edge routers to provide connectivity between our spokes within the same region. In this example diagram, we have our standard hub and spoke topology, and we want to provide connectivity between spoke 1 and spoke 2. Remember that even though we have VNet peering from our spokes to our hub, VNets are not transitive, so these spokes would not be able to communicate by default. By advertising a default route or summary route from on-prem, we can allow spoke 1 to talk to spoke 2 by hairpinning traffic off these Microsoft Edge routers. As we continue to add additional spokes, this default or summary route would provide that same connectivity, so this is a common default method for customers to start with. The challenges with this method is that it provides any-to-any communication between all spokes, which is something we may not want. We may want to insert a firewall between certain spokes or even prevent connectivity completely for specific environments. Additionally, these edge devices were never intended to provide transitive traffic flows, as they were designed for highly multi-tenant onboarding. There is no guaranteed bandwidth allocated for this transit behavior, and this method is not officially documented by Microsoft. Finally, these traffic flows are often suboptimal due to the hairpinning nature. Spoke-to-spoke traffic must vector down to these routers, which could be close to the region, or may exist somewhere else on the Microsoft network where an enterprise circuit has been provisioned. If customers need to prevent this any-to-any behavior, user-defined routes must be configured to black hole traffic or inject a firewall into the path. Additionally, advertising a default route into Azure can cause longer-term problems as customers look to leverage more advanced PaaS services. The only bandwidth limitation in this method is the sizing of the ExpressRoute gateway. Since the traffic is hairpinning off the Microsoft Edge routers rather than the circuit itself, the size of the circuit is irrelevant. Only the ExpressRoute gateway is in the traffic flow and represents the only potential bandwidth bottleneck. Again, This method is not recommended by the Azure product group as there is limited control for performance, noisy neighbor issues, and traffic visibility. A second option is to provide spoke-to-spoke communication within our hub. As we mentioned previously, VNets are not transitive by default. However, we can leverage an NVA with UDRs to facilitate spoke-to-spoke communication. We would create route tables in each of our spoke VNets and create user-defined routes with the next hop of our NVA to reach out to the destination. This method of transit is great because it provides us a more granular approach with additional security the NVA provides. We can be specific about what we want to allow through, as well as get some deeper level packet inspection based on the NVA chosen. The challenge with this approach is managing this at scale. As new VNets are created, we have to constantly manage these spoke route table entries to include the new address space. In addition, we may also need to manage the policies in our NVA to allow communication to flow through. There are some other considerations around NVA high availability, failover times, and source NAT that we may also have to manually configure in order to make this option work. So it begins to become a challenge as our environment scales. The third option for connecting spokes is VNet peering. VNet peering is a one-to-one mapping of one VNet to another. This is the best possible option for optimal traffic path and bandwidth, as it leverages the Azure backbone, and there are no limiting factors in the way. The challenge with this method is scaling. Since this method is a one-to-one mapping of spokes, each spoke would have to be peered with every other spoke to facilitate communication. While not a bad method with a handful of spoke VNets, this quickly becomes an interconnected mess at scale. The options we just reviewed cover the transitive mechanisms for intra-region. However, this changes a little bit as our spokes communicate across regions. In the case of leveraging the Microsoft Edge routers for hairpinning, the default or summary route is not required as this traffic flows by default. Keep in mind, we would still need this for our region-specific traffic, but cross-region traffic would follow our same any-to-any connectivity. Our second option of leveraging an NVA within our hub could extend across regions. However, typically customers build another hub and spoke environment in their secondary region, which would require additional routes and peerings. This unfortunately just provides us with more things to manage as we scale out. The third option of direct VNet peering is also available cross-region, although it's referred to as global VNet peering and comes at a different price point. We still have the same challenges of one-to-one mapping, so the challenges with this method still apply. Now, Microsoft recognized customers were facing challenges with transit routing and the constant management of UDRs, and announced a new service called Azure Virtual WAN to help address some of these items. Virtual WAN is something that has been developing since 2018 and has gained a lot of maturity over the years. The idea was essentially, how can we make this easier for customers at scale? Azure Virtual WAN, it's still built on hub and spoke. However, the hub becomes a managed Microsoft service. Microsoft takes care of all the hub VNets, and then customers just attach spokes to the respective hubs in their respective regions where the workloads live. Azure Virtual WAN would provide all of the interconnectivity under the hood, and customers no longer had to manage all this. While this was a step in the right direction, there are still some challenges here. The reality is that Azure Virtual WAN is an entire platform. While the automation of UDRs was a portion of the solution, many other features got bundled into this platform as it grew. On-prem to on-prem traffic capabilities, support for large-scale branch connectivity with zero-touch provisioning, and many others. So if you want to leverage this service, it's an all-in type of deal where you have to buy into the entire platform. Many customers wanted pieces of this functionality, but didn't want to have to buy into the whole platform. Another challenge comes in when customers need to scale to another cloud. This platform works well in Azure, but does not exist in any other cloud today. As an architecture, it did not provide a repeatable method that could be reused when expansion to other clouds was required. There are also some issues with virtual WAN in terms of flexibility. Since the hub VNet routing become part of the managed service, the ability to customize these elements is taken away. Customers were no longer able to leverage third-party devices in their hubs, for example, for filtering, and instead were forced to use the native Azure firewall. In addition, the any-to-any connectivity that Azure Virtual WAN provides began to cause problems with routing limitations. For example, one limitation that currently exists with ExpressRoute is that a single gateway can only advertise 200 routes from Azure to on-prem over private peering. As Azure Virtual WAN was introduced into the picture, with any-to-any routing, it increased the number of routes being redistributed across the environment. Without the ability to granularly control these route advertisements, these limits became more of a danger for customers. While limits will inevitably be raised and offerings continually improved, Virtual WAN as a platform provides a step in the right direction for architecture, but is still missing a few important pieces. Enterprise customers want an architecture that can support scaling both within a cloud and across clouds without having to sacrifice the granular control and visibility of their networks. Thank you for taking the time to listen to this section on Azure fundamentals, and I hope this helps highlight some of the nuances across cloud providers.